What's a CNA? How does it work?
Okay, so let's get started for today's class. So we started talking about SRAM, right? 6 transistor static random access memory. We'll be giving a bit of quantitative treatment today. We'll derive some equations and all, which will set up for homework 2. That's why I delayed the homework 2 posting. I thought after today's class, you'll be prepared to work on homework 2 problems. Okay, so these are the few equations that you may need to use for getting a quantitative idea about SRAM operations. So we talked about at the beginning of the class that CMOS transistor, right, or an NMOS or PMOS transistors can be described by these two equations. So at the beginning, when your drain voltage is low, drain to source voltage is low, the first is gate voltage should be sufficiently high to turn on the transistor, right? That's the fundamental. If it is low, then it is sub-threshold operation, current is very low. But yes, when gate voltage is sufficiently high, drain current can be given by these two equations. One is this low drain voltage will give triode or linear. And then there is a saturation region where current becomes independent of voltage. Unlike Ohm's law, right? Ohm's law doesn't say that, but that's what we assumed, and we'll be assuming pretty straight without any channel length modulation, pretty much like a square law standard equation in today's derivation or throughout the course, just to make your calculations simple. What I mean is there can be some slope here, but we'll ignore that slope. Okay, and these are the two regions. Linear region. This is linear because drain voltage comes into the equation. You can typically ignore the square, but yeah, generally this is the full equation without any approximation. And this is the full equation without any approximation for square law region. And the boundary is VGS minus VT. This is the boundary between these two equations. At that point, both the equation will give you the same current. Okay. Now, from previous class, we talked about for SRAM read and SRAM write, right? You have to size the transistors properly. If you don't size those transistors, you may fail in write. You may not be able to write. You may fail in the read in the sense read can be destructive. Ideally, we want read should be non-destructive. You can read any number of times without changing the content. So if you don't follow these ratios, some of those ratios, these numbers are like it's a ballpark number. These are not the exact limit. These are not theoretical number. We'll derive today some of those numbers, but this is just to give you an idea. So, so there are 3 types of transistor we talked about in the SRAM cell. One is this pull up PMOS, P1 and P2, pull down NMOS, N1 and N2, and the access transistor A1 and A2. You turn on access transistors only to read or write. For storing, the storage element is this back-to-back inverter. This P1, N1 forms one inverter, CMOS inverter, and P2, N2 forms another CMOS inverter. So they are connected in the back-to-back fashion. That means more like this. So this is the inverter, the P1, N1, and this is the other inverter, the P2, N2. Right? So which one will be Q? This side will be Q or this side will be Q by looking at this diagram. So look at the T1, N1. Output of P1, N1 is Q. That means this is Q. This is Q1. This is the output of an inverter. This is the input of an inverter, right? This is Q1. Make sense? Okay. So that's the storage element. This back-to-back inverter is also called latch. It stores the data. As long as power is there, that value will not going to change because this is a positive feedback going on. Or in other words, those Q and Q bar, you can think about 2 capacitors, which will be in femtofarad range. So even if charge can be lost through leakage, say here leakage can happen through N1 or A1, but this P1 is always on, right? So for example, Q equal to 1 means P1 is on. So P1 will replenish that lost charge. So you will never lose information as long as there is a power. Okay, so that's the advantage of static RAM. So today we will talk about some of those ratios, that how you should design those ratios exactly so that you meet some of the design spec. Design spec can be that how much read disturb you can tolerate, right? How much time you can allow for reading and writing. Those are the spec, right? So you want to do read and write in pretty fast. You want to do it in nanoseconds range, right? So today we'll see, is read and write symmetric? Is the same amount of time you will take to read, same amount of time? If not, who will be longer? Who will take longer time? Any guess? Reading will take longer time or writing will take longer time? So that's an interesting question. Answer is reading. Reading will take a little bit longer time, and we'll talk about why. Okay, so we'll see some of those details as we go in the math part of it. Okay, so let's talk about one by one. So start with the read operation. Let's assume the SRAM cell is storing Q equal to 1. That is your initial state. This is the element it is storing. And okay, so you want to read 1, right? This is your operation. You want to read that value, that Q equal to 1. So the storing is 1, and in this case, Q will be, so based on what it is storing, right? One of the transistors will be off, another transistors will be on. For example, here P2, N1 will be off, P1, N1, N2 will be on. Right? Because it is storing Q equal to 1, right? Here. So definitely N1 cannot be on, because if N1 is on, this will discharge. So this is off, P1 is on, okay? And N2 is on because gate of N2 is Q equal to 1, which is high voltage. So gate of N2 is high voltage, so N2 is on, but again here it is 0 volt anyway, discharged at that point. Q bar is discharged. So even if it is on, it is not discharging any, or it is not carrying any current. This is the steady state condition that you are holding 1. Now you want to start reading. What is the first step in reading? Yes, precharge those bit lines first, right? Precharge both the bit lines to same voltage, VDD, for example. So this is the first step. Before you start the read operation, you precharge bit line and bit line bar both at VDD. Okay, so this phase is called precharging. And next, word line. Then you turn on the word line, right? So when you turn on the word line, those access transistors will be on. And now you will see one of the bit line will discharge, and based on that, you will decide is it storing 1 or 0. If bit line is discharging, then it is storing 1. Then it is storing 0. If bit line bar is discharging, then it is storing 1. Okay. So, or in other words, you can see when A1 is on, this is VDD, this is also VDD. So there will be nothing going on here across this A1 transistor, even though it is on. Both side is at supply voltage VDD. So nothing is going to happen here. So this bit line will retain its charge VDD. But whereas this bit line bar, it is charged with VDD. Now, because this transistor is on, this is 0 volt, this will start to discharge. Or in other words, you can think it like this, all this Q, right? Q and Q bar is basically a capacitor, right? So it is a effective capacitor, very small in picofarad range. So what is going to happen? This capacitor was discharged, right, at the beginning of read operation, right? When you turn, just before turning on the word line, this capacitor was discharged because this node voltage was 0. The moment you turn it on, these two capacitors will do some charge sharing. Okay. Now, the moment you turn it A2 on, this C bit line, right? This will start to charge this capacitor CQR. Make sense? This is on. So this voltage will keep rising. And what is going to happen if this voltage rise? N2 will start conducting now. Earlier N2 was on, but it was not conducting because this voltage was 0. So 0 to 0, there will not be any current flow. Now, the moment this capacitor is beginning to charge, right, this voltage is rising. VQ bar is rising. It is no more 0. The moment VQ bar is rising, N2 will be conducting current. Now, will N2 conduct current in saturation regime or linear regime? Question to you. The equation, right? This N2 will start to conduct. Now, question is how you will describe that current. Will you describe the current using square law, saturation, or will you describe this current using linear law of transistor? Linear. Because the drain voltage is low, right? It is 0, it can be 0.1. So VDS is very low. So you need to use this appropriate equation, right? Because this equation will be linear. You'll describe the equation for N2 with linear. How about A2? How will describe the equation for A2? Well, both are on. For A2, right, one side is VDD, high voltage, and that VDD will not drop immediately because this is a big capacitor. If VDD is say 1 volt, this may drop to maybe 0.9 volt. So VDS will be very, very high for A2. So this will be in saturation region. So that's what you need to be careful. When you write the equation, you need to know, are you operating in this linear regime or are you operating in the saturation regime? And based on that, you apply the currents. Okay, so that's the first part. Okay, this A2 and N2 are in competition. So N2 wants to discharge this Q2, right? And A2 want to charge this capacitor Q. So what will happen with time? You will reach an equilibrium point. And how is defined by equilibrium here? Equilibrium is this capacitor will no more charge. It will set a voltage, say Vx. At this point, so initially what happened? A2 was charging CQ. The voltage was rising, and then N2 is discharging VQ. So at some point, you will reach an equilibrium where no current will go through the CQ. The voltage across this CQ will be fixed. Or voltage at Q bar node, right? It will be fixed. So this is CQ bar. Sorry, this is not CQ. Just this CQ bar, because this is the Q bar node. This is the Q node, right? So you will reach an equilibrium, and the voltage there will not be 0. Equilibrium voltage will not be 0. What is your best guess for equilibrium voltage? Will it be close to VDD? Will it be close to 0? Or will it be close to threshold voltage? Are you following what I'm saying? So you will, this is on, this is also on. This is VDD suppose 1 volt. Initially this voltage is 0. It will gradually rise. If it rises beyond threshold voltage of a transistor, right, then the inverter will flip or you will change the content of the SRAM cell. So we don't want to allow this Q bar to rise high voltage. Definitely lower than the inverter threshold voltage. Okay. So this is the condition. VQ, we'll know it invariably VQ will rise. But that Vx voltage should be lower than the threshold voltage of a transistor. I mean, more strictly, it should be lower than the threshold voltage of the inverter P1 N1, right? P1 N1 has a voltage, after that it will flip. So it should be lower than the inverter threshold voltage, but for safety margin, this is the strict requirement. The threshold voltage, transistor has a threshold voltage, say 0.3 volt. So VQ bar should not be more than threshold voltage of a transistor. So that's the constraint, mathematical constraint for success of read. That means you need to find the equation of VQ bar or equilibrium value of VQ bar, right? And then see whether it be more or less than VT. So that's how you can see read stability, and that will give you the cell ratio. What should be the cell ratio? Up to this point makes sense qualitatively. So now let's write this equation. So when the word line is selected, the access transistors will be turned on, both the access transistors are on, and causing current flow through A2, N2. So this is your current flow path. This is the only relevant part of the circuit. And since initial voltage is 0 VQ, so current from the bit line will directly go and charge this capacitor, and after some time NO2 will start to flow, and then you will not further charge this capacitor, and you will reach an equilibrium point. So equilibrium will be reached after some time when CQ is charged to a voltage VQ at which IA2, current of A2 and current of N2 equals. Make sense? So first we're talking about transient point, right? We're talking about say in picosecond or after say 1 nanosecond of turning on, right? Very early stage, this A2 is conducting more current, this N2 is conducting less current because it starts with 0. But after some time, say after 1 nanosecond, both A2 and N2 will carry the same current, and that is called equilibrium point. So at this point, there will not be any more charging on this capacitor Q. The voltage will be stabilized at Vx, and that stabilized voltage should be less than or equal to Vt. How long you want to stabilize? How long you want to wait for read? How long you want to keep it at Vx for read operation? What determines how long you have to wait for reading? Anyone?
Is it an RC constant?
Not really. You have to look at this one, right? So this one is drooping. And for sense amplifier to sense, you need some voltage difference. This is always keeping at VDD, say 1 volt. This has to go, say 0.8 volt or 0.9 volt. So that this 100 millivolt delta that sensing amplifier will amplify. If it is say only 50 millivolt delta, then sense amplifier will not be able to do that. So you have to wait for bit line to go down, and that process is slow because bit line is a huge capacitor, right? Bit line capacitance is in picofarad range, so even dropping 100 millivolt at the bit line will take some time, and that's why read operation is slow, because read operation relies on discharge of the bit line, which is a big capacitor, whereas write will not. We'll see that. Write doesn't depend on discharge of the bit line capacitance. So read is slow typically because you have to wait for bit line to discharge to some extent, and that discharge depends on the current of those NMOS transistors as well as bit line capacitance. Question, comments so far? Make sense? Why read has to be slow? Because you have to rely on big bit line capacitor to discharge. So now question is, we have to find equilibrium value of VQ bar, and you have to check whether the equilibrium value is less than the threshold voltage value. Otherwise, there is a chance that you will flip the bit. So let's look at how to find the equilibrium value, right? So that's why we will do this. So to make sure that it is a non-destructive read, VQ must not exceed the threshold voltage of the inverter, or more specifically or more stringently, threshold voltage of individual NMOS transistors. So that is the criteria we'll be using to make sure that it is a non-destructive read. Okay, so let's look at this equation now. We talked about which transistor will be operating in linear and which at the, so let's think about equilibrium point, right? So right now we want to do equilibrium analysis or equilibrium value of this node's voltage. So which one will be operating in the linear? N2. So when you talk about equation for N2, we will have to use this equation. This is a linear mode equation, right? Mu, electron, W by L of N. N means NMOS. P will be PMOS, and access means I will use A. So these are the consistent symbols I will be using. For access transistor, I will be using A. NMOS, I will be using just N. And for PMOS, I will be using P. So this is for equation for N2. Right? So what do you think? VDS will be, what is the value of VDS? Here. VGS, what is the value of VGS in this equation? In terms of, so you have supply voltage. Supply voltage is constant. Threshold voltage is constant. So you have to use those values right here. So VGS will be supply voltage. Because this transistor, right? We're talking about this transistor. What is the value here? Q equal to 1. Q equal to 1 means VDD, supply voltage. Source is grounded. So you have to appropriately substitute. And this derivation will be very important because in homework you will be solving questions like this. Okay, so VGS is supply voltage. VDS, can anyone tell me what is the drain to source? Will be VQ bar. That's what you want to find out. So these are the substitution you will make. VGS, VDD, supply voltage, which is a problem statement will have given this value, say 1 volt or 1.2 volt. And VQ is the one you want to find, equilibrium value. This is the equilibrium value of node Q bar. How about this one? So for access transistor, right? This is another transistor A2, which is in contention. So this access transistor, VGS will be, what is VGS for this access transistor? Anyone following this? Yeah, it will be VDD or lower than VDD?
VDD minus BQ bar.
BQ bar. You have to, because VG, right? Gate voltage. Gate voltage is at VDD because you turned on the word line. And source is this point, which is VQ bar. So here, VGS will be VDD minus VQ bar. So plug it in and make sure that these two currents are same because we are talking about equilibrium condition. Under equilibrium, these two currents has to be the same. So you equate these two currents. This is for NMOS, this is for PMOS. You can see mobility, both are electron mobility, cancels out, Cox cancels out. So that remains your equation, right? You can simplify this equation and it can be rearranged this way. So this can be starting point. Even if you don't want to do this math, you can start with this for many of your homework points, right? Because this gives you the ratios. What should be the ratio so that VQ remains under some threshold. Okay. Any question on this derivation? Okay, so that will be your read condition. During read condition, this condition, you can start and plug in some numbers. For example, if VQ less than VTN, what will be my ratio? And this is the x-axis, which is the ratio of this transistor and access transistor versus NMOS transistor. If access transistor becomes stronger and stronger, right, read will be unsuccessful. This is the inverse of cell ratio, access transistor by NMOS transistor, right? So if access transistor is stronger, your VQ, right, VQ will rise. So VQ is normalized, VDD is a constant, VT is a constant, right? VDD say can be, say, 1 volt, threshold voltage can be 0.2 volt. So that value is fixed. So this is the VQ, which is the variable which will rise according to this equation. You can simplify this equation a little bit more. You can write it VQ by VDD minus, so you can see this is a square, right? Take a square root and rearrange the term, so you can write it like this. So you can exactly find what is your equilibrium VQ for a given transistor ratio. You don't need mu, Cox, because they get cancels out. So as long as you know the ratio of those, sizing of those transistors, access transistor and MOS, you know exactly what is your VQ bar voltage or what is the read disturb voltage. So VQ bar here is a read disturb voltage. And we want VQ bar should be as low as possible. Or in other words, we want cell ratio should be as high as possible. So this is inverse of cell ratio again. So we want ideally should be here. We should operate it here. VQ bar should not go say 0.1 or something like that. Or access transistor has to be much smaller than the NMOS transistor. That's what we discussed qualitatively last class. So today's class we are giving you a quantitative picture that how small it should be, and you can find from this equation. Any question here so far? Okay, so this is your starting point. You can think about, after equating all those currents, one is linear regime, saturation, and there's a lot of details, right? All these details can be captured by this simple equation. Here, no approximation has been taken. It's a direct equation, okay? So you can also rearrange these terms. If you want to find VQ, you can use this equation. If you want to find ratio, you can use this equation as well. Right? So for here, VQ is the unknown. That okay? Read disturb voltage is 0.1 volt, 0.2 volt. You can find it out from this. Or if you want to know that, okay, my read should not fail, what is the criteria? Then VQ, maximum value of VQ can be threshold voltage. It should be lower than threshold voltage, so, but let's put the maximum extreme case. Then what should be my ratios? Okay, because everything has trade-off. For example, yes, you can make access transistor weak, very, very weak, so that this equation always holds. But what is the penalty? If you make access transistor very weak, what is going to happen? So this equation says that access transistor should be weak for it to be successful, which makes sense, right? Because if you look at this picture here, if this transistor is weak, this transistor will dominate and Q will be always close to 0. But if you make access transistor weak means low current. What parameter in the memory operation will suffer? Huh? Time and also write. Both of you are correct. So one is read time will be very, very small. Sorry, very, very large. Right? You cannot read. So if current by the access transistor is small, then it will take longer time to discharge the bit line. Well, bit line has to discharge. It has to go to certain voltage, right, to create the difference between this bit line and bit line bar. So that process will be longer if you make access transistor weak, right? So that's a penalty that you want to read SRAM, right, very fast. SRAM is a fast memory. You want to read it in a couple of nanoseconds. So just by making sure that it is non-destructive read, you cannot make it slow. So that's one bound. Another bound is write, as you said. So if you make this is too weak, it may not be able to write. Because for writing, this has to be strong. We'll see as we go forward. But I hope up to this point is clear. So now let's summarize this. I think we talked about this timing diagram as well, that okay, read starts when you turn on this word line. Right? So this is your starting point of read. And when you turn on the word line, this VQ bar will rise. It will saturate, it will reach an equilibrium value. That equilibrium value has to be lower than the threshold voltage. Otherwise, there will be a flip or content will be lost. One of the bit line will remain at VDD, it will not change at all. The other bit line will decay, and that delta V is very critical. Because that's how sense amplifiers become very important, right? So sense amplifiers will reduce the sensing time. If it is a very strong sense amplifier, it can sense maybe 50 millivolt difference, then you can read faster or your latency will be small, right? So that's why this is another very important component of memory array, that you want to read fast, then you need to design a strong sense amplifier. Otherwise, you have to wait for longer time, okay? So you have to wait for longer time for the bit line to discharge. For example, at the beginning, when 1970s SRAM was first proposed, that time sense amplifier was not there. And you can see the timing will be in maybe micro or millisecond, right? So later sense amplifier was invented because of this need that I want to sense faster, readout should be fast. So that's why it will speeden up the read process. So if you want to give a quantitative treatment that how long I have to wait, so that's where this, you have to see for read one operation, how long I have to wait. So VQ will rise from 0 to Vx, and supposedly it should be lower than the threshold voltage, otherwise it will be a destructive read, right? So this condition is first, and assuming that IA2, right, with the access transistor current, reaches its equilibrium value relatively quickly. So this is the time needed to reach the equilibrium. After this point, right, this flat region is what is decaying your bit line voltage. So how long this flat region should be, that decides how long your read time should be, read latency. So we'll make this assumption that okay, A2 is operating in the equilibrium point. Equilibrium point means VQ is equal to Vx, whatever value that is. With that, what is the time, okay, to discharge this capacitor? So you can use this capacitance equation. Current times time is a charge, right? Current is charge per unit time. So when you say current times delta T is the time required to discharge this bit line, is Q. So this is equal to Q of the bit line. Q equal to CV, right? It's capacitance, basic capacitance equation. Capacitor means it holds charge, it gets the voltage. Q is the charge it is holding, and so, or in other words, we can say, to start in a high school question, right? So capacitor Q equal to CV, also equal to delta Q equal to C delta P. Change in voltage is change in capacitance. This is a more fundamental question for capacitance. Okay, so this is the absolute value, this is the relative charge. If I have a change in voltage, there has to be change in charge. That's what it is. This is your change in voltage, this is your change in charge. So that's the charge bit line will be losing, and that's how we will sense the amplifier. So this is your current, or sorry, time, latency, how long you have to wait to have your readout value. So you can clearly see if you want to make readout faster, you have to make access transistor stronger. IA2 should be high. But if you make access transistor stronger, you can flip the content. So these are all design constraints, right? You have to optimize. Bitline you cannot do much because bitline capacitance has to be large. You can all you can do is you can subdivide your array into multiple squares. Instead of making a big square, you can make it modular to make bitline capacitance a little bit small. So these are the typical things you can think about, and delta V is the constraint defined by your sense amplifier. That how much small voltage I can sense. Is it 100 millivolt, 200 millivolt? So we'll see a couple of problems using this kind of equation, using, so here, the difficult part here is finding IA2. Because what is IA2? IA2 is your equilibrium value of current. That means you need to know what is equilibrium voltage, VQ. So you have to find all those things to get exact estimate for delta T. Okay. So that's pretty much I would like to say that bitline capacitance is large, and that's why delta V discharge will take longer time, and that's why read is a little bit slower than write. Okay, so let's summarize what you learned for SRAM so far. So read 1 operation and read 0 operation will be exactly the same because it's symmetric, right? When you talk about read 1 operation, we focus more on the Q bar node. When you talk about read 0 operation, we'll focus more on the Q node. So, but all this equation, all the discussion also applies for read 1 as well as read 0 because these are symmetric. The component delta T of the read time is relatively large because bitline capacitance is large. Discharging bitline is a time-consuming process, right? So that's why read is slow compared to write. Slow means still in nanosecond, say 4 or 5 nanoseconds. Okay, there is not just bitline discharge time; it also takes some time to rise the word line. Because word line is going from 0 to VDD, and word lines are also big, entire row. So both this time constitute total time for read. Okay, now let's look at the write operations. But any question here on read part? Anything that makes sense to all of you? Okay, now let's look at for quantitative treatment for write, and after that we'll solve few problems and it will be all set for homework 2 after that, okay? So let's look at the write operation. So assume that your VQ is 1 again, you are holding cell state 1. Now you want to write 0. Right? Because if you're holding 1 and you want to write 1, nothing happens there, right? But if you want to flip the cell, then what is going to happen? So again, your start is, whenever you want to write 0, first step is condition those bit line. So put 0 on the bit line, which I put bit line. So whatever data you want to write, you put it on the bit line and complement on the bit line bar. If you want to write 1, you put bit line 1, bit line bar 0. It's different than read. Read both cases, right? Bit line and bit line bar both goes to VDD, high voltage. But for write, you choose. So yeah, bit line will go to 0, bit line bar is 1 because I want to write 0. That is the first thing. Second thing, I will turn on this word line. So access transistors are now on. Now, what is going to happen? There are 2 regions where computation will take place. One is here, because here, right, this is on, this is on. Whenever Q equal to 1, P1 has to be on, right? Q equal to 1, N2 has to be on because the N2 gate is Q equal to 1. Okay, so now what is going to happen that these two will compete to keep P1 wants to keep Q to be 1, right? Because anytime Q loses charge, P1 is on, it will immediately replenish that charge, lost charge. But this access transistor 1, A1 wants to discharge it because one end is 0, another end is VDD, right? So this will try to discharge. So this is one competition, that this wants to discharge, this wants to keep it at charge. And this is another competition, A2 and N2. So here Q bar is 0, here it is 1, just like in a read condition, right? When you turn it on, if you raise this voltage, then it will again flip. But that is what we want right now. Right now we want to flip. Right? Right now we want to write. Write means I want to flip. So which competition is more important? Or which one you think will be winning? This P1, A1 competition or A2, N2 competition? Which one do you think will decide right? A1, P1. Answer is correct. Because this one, right? This one will be losing, right? We talked about during read. Just now we talked about. We'll size them so that this A2 cannot win against N2. Right? So this one, we know that A2 is going to lose. It will not able to flip. So from right perspective, what is important is this one, P1 and A1. Competition between access transistor 1 and PMOS 1. With this, from read point of view, we don't want to flip. And if you don't want to flip, it will not be able to write it. So this is irrelevant from the point of view of writability. From the point of view of writability, this PMOS and access transistor competition is more important, or you have to focus that part a little bit more. Is that make sense to all of you? Because there will be multiple choice questions. You will be tested with all those details. Okay, so now VQ decreases below the threshold voltage. If VQ, this right, has to decrease, now it has to go at least below the threshold voltage of the transistor so that these regenerative actions take place. Because the moment VQ, right, it is right now VDD. If it goes to lower than the threshold voltage can be say 0.2, 0.3 volt. You have to drive it down lower than that value. Only then this inverter will kick in. So look, couple of things here. There is no need for bitline discharge here. Right? All you need to do is discharge this node. This node capacitance is in femtofarad. It's not in picofarad, or this is a very small capacitance at Q equal to 1. Right? So that capacitance discharge takes less time because it is femtofarad. Orders of magnitude less time to discharge this node capacitance. And that's why write is faster. Read is slower because read requires discharge of bit lines. Okay? Any question here so far? Yes.
So you're saying for the bit line, not the side, we size P1 and A1 so that A1 wins, and for the other side, A2 and N2, we size N2 so N2 wins.
N2 wins for read.
And then for write, A1 wins.
A1 wins between these two. So in other words, if you want to design a safe design, the PMOS should be the weakest, then access, and then NMOS. So NMOS, pull down NMOS should be the strongest in your design. That's the rule of thumb. But everything has pros and cons, right? If you make A2, A1 or P1 very, very weak, then you may lose charge much quicker. Because P1 purpose is keep Q1 at always at 1. Okay, so any leakage, for example, there is always leakage going on. If you make P1 very, very weak, then your data retention voltage, right, will be very, very small, large. You cannot go down to lower data retention voltage. So yeah, so there is a lot of design, but did I answer your question? Yeah, so you have to have P1 weak, A1 stronger than P1 to make sure that write happens, and write will happen through this path, not through this path. But this path we already discussed from read point of view has to lose. This will not drive the writability. Writability of the cell will be driven by this P1 and N1 combination. Okay, let's look at some equation now. So what do you think? Equation means you have two choice. You have to know saturation or triode. So which one you think in this? And also at equilibrium, we'll be solving. We'll not be solving the transient part of the equation. We'll be solving what is the steady state or equilibrium part of the equation. So at equilibrium, this node will stay at a voltage. So Vx, right? Vq will not be at VDD. It will be stay at Vx, and that means P1 current and A1 current has to match, right? So at equilibrium, what do you think? Which one will be saturation? Which one will be? Both are on. Both will be saturation. Both will be triode. One will be triode. One will be saturation. Which one do you think? Let's talk about which one will be in saturation. P1 will be in saturation. A1 will be in the triode or linear. The reason is this voltage, right, has to go down low, below the threshold voltage. Threshold voltage is 0.2 or 0.3. So it has to go to very low voltage. When it's low voltage VDS, because this bit line, right, 0, this is not going to change. It will remain at 0. Even if there is some charge goes on maybe 0.05, 50 millivolt will go up. This bit line voltage will not go up much. So this will be, say, 0. This will be, say, 0.3. Then this is triode. This will be in saturation. Okay, so that's the thing, and then you can plug in these numbers, right? So we will be assuming so VQ bar will not rise above VTN. So writability, right? Writability will be ensured if this voltage goes down, so that this inverter flips. Because this inverter is right now at this P2 and 2 is at output 0, right? So if it goes down, this will flip. So more stringently, circuit designer designed that it should be lower than the threshold voltage of this NMOS transistor. Because right now NMOS is on. That's why this node is 0. If you go below the threshold voltage of this NMOS transistor, then this NMOS will be off. And then this node will start to rise. But the moment it is off, right, this bit line will immediately charge it. So that's why the criteria for what we'll be using in problem solving is your equilibrium VQ should be less than the threshold voltage of the transistor. Makes sense? Okay. So let's look at some of those equations. So this is the simplified diagram, which is the relevant part. This is the PMOS P1. This is the access transistor A1. They are competing. Bit line voltage is 0. And this is VQ, which is initially at VDD. The moment you turn on this word line, V word line is VDD. This is VGS, right? For A1 will be VDD. And VDS will be VQ. So you know this is in linear region, this is in saturation region. So okay, so right, 0 operation will be accomplished by pulling the node Q, right, to initiate the regenerative action of the latch, because this is a back-to-back inverter. So you have to pull down this Q to enough low voltage so that this latch operation starts, and VQ should be at least lower than the transistor N2's threshold voltage. At this point is going the gate of N2. So N2 should be turned off to flip, right? So that's why this is the criteria, threshold voltage of the NMOS transistor, that you have to pull down this node voltage from VDD to at least threshold voltage so that inverter flips or the write happens. Yes?
Are we waiting VN1 or for VN1 to be at below the threshold voltage during this process?
So VN1 is off already.
Okay.
So this is not taking part, right? Only P1 is on. So yeah, so N1 will not be taking part in any current conduction. Yeah, because P1 is on, N1, so if we go here, right, N1 is off.
Right.
So this is on. So I want to turn off this N2 so that it flips.
So N2 will eventually turn off
Yes.
after a period of time.
Yes, after a period of time defined by the voltage at Q.
Okay. And that time is significantly less than.
Yeah, because this capacitor, right, Q equal to 1 is holding on a capacitor. That capacitance is very small. Cell capacitance is in femtofarad. Okay, so it will require much lower time compared to bit line discharge.
Gotcha.
Yeah. Okay, so this CQ, right, CQ is a very small capacitance, which is in femtofarad. This bit line is a big capacitance, which is in nanofarad or picofarad. So that's why there is a difference. Okay, so these are the step-by-step process. I suggest, I'm not going through them. Please read through them because this gives you full idea what is going on, right? What is required to toggle, because you have to toggle this transistor. But the main part here is at equilibrium, IP1 or current of PMOS 1 has to be equal to current of NMOS A1, and that equilibrium VQ should be lower than the threshold voltage. So if you want to equate these currents, you need to know who is operating in what regime. So P1 will be operating in saturation, but this voltage is low, right? If this voltage is low, N or A1, access transistor 1, will be operating in triode region. So that's the critical thing to understand, right? Because once you know this, we can equate those equations. For example, here for P1, right? This is the P1 transistor. Its equation is given by mod. Mod I am using because your current equation, you can always use VGS minus VT square. But for PMOS, threshold voltage is negative. That's why we are using mod here. VSG. What will be the VSG in this case? What is source? Source is this. VDD. Right? Gate is at 0. So VSG for P1 will be VDD. So now this equation is in a known form, which is VDD minus VT square. How about this one? Access transistor A1. This is the equation, right? For triode. Your VGS minus VT into VDS. What is VGS and what is VDS? That's what you need to figure it out. What do you think? What is VGS for access transistor? Gate to source. If you look at here, gate is at VDD, source is at 0. So gate to source is VDD. So as simple as just look at the circuit. Here gate is at VDD, source is at 0 because bit line is always at 0. So this is VDD. How about VDS? What will be VDS value? Drain to source or from here to here. It will be VQ. Yeah, so this is where you have to pay attention, right? So VDS will be VQ, not VDD. Because this is VQ, this is ground. So plug it in now in this equation, equate them, right? Because if you have to find what is the equilibrium value of VQ, you have to equate these two currents, and that will give you an equation like this. The VQ value depends on ratios and also mobility ratios now. Because earlier mobility ratio was absent in your equation because both are electron mobility, right? Access transistor also electron, pull down, and MOS also electron. So mobility was not there. But now PMOS has lower mobility and MOS has high mobility, so this mobility ratios comes in your picture. Oxide capacitance remains same. Oxide thickness, area of all the transistors remains same, so that's why that cancels out. So this oxides cancels out, but mu and mu p remains. And if you rearrange those terms, this is the one you can remember, right? So if you want to find VQ for a given ratio, plug it in numbers, find what is the VQ, it will go, and check whether write will take place or not. Because if VQ turned out to be higher than threshold voltage, then write will not take place. Okay. And in other case, you want to find the ratios for write to take place. Then in that case, what value of VQ you will put? At least. So in order to write to take place, what value of VQ should be? At least. Not really. It has to be the threshold voltage of the transistor, right? Because that's what the criteria, stringent criteria we'll be using. Yes, you may be right, because if your butterfly diagram, if the metastability is 0.5, right, it can take place, but that there is a chance. Whether it will, sometime it may take place right, sometime it will not. But if you set it up to threshold voltage of a transistor, definitely right will take place. And that's why the good designer, right, good SRAM designer will choose or set this VQ at least to VT. Okay, so now if you can plot writability curve, x-axis is the ratios, the the PMOS ratio versus access transistor ratio. So if PMOS becomes stronger and stronger, write will not take place because VQ is rising. I want VQ to be low, right, to write to take place. VQ starts at high voltage, VDD, not like read. But here you are starting with high VDD. So you have to pull down the VQ to a lower voltage. And that for that, your PMOS should be weak. Okay? Questions, comments? Okay, so I think we'll see a few problems. So yeah, I think you can rewrite the same equation. If you want to find the W by L ratio, you can use this equation. If you want to find VQ, you can use both. Both are same exactly. Okay, so to conclude, your write time is smaller than read time because here we are talking about discharging the cell capacitance, which is CQ. CQ is in the order of femtofarad. That's why write is faster. And mobility ratios you have to take into account for calculating your writability as well. So for write, the main time constraint is not sensing. It is the word line that you have to turn on the word line. Right? So the word line rise time will constitute the majority of your write latency. The moment you turn on the word line, it is basically flipped, less than a nanosecond, for example. But for read, you need to wait for 4 or 5 nanoseconds just to bit line to discharge. Okay, let's solve a few problems. I think we'll be done after that. So I have planned at least 3 problems. So let's read the problem statement and see whether you understand the problem statement. So we're asking maximum allowable, right? Because if you keep access transistor very, very large, you'll never be doing a non-destructive read, right? If your access transistor is very, very strong, it will be a destructive read, right? That's why what is the maximum allowable we are saying, so that read is non-destructive. So for being non-destructive, Q and Q bar both should not go more than the threshold voltage of a transistor. We're assuming threshold voltage symmetric. That's the pretty much standard assumption for NMOS and PMOS. Magnitude is same, 0.35 in this case. And W by L ratio for NMOS transistor is 2. So that means if it is 65 nanometer node, what will be L? L will be typically 65 nanometer. You'll try to size the transistor to be smallest so that you can pack more transistor, right? It's a digital electronics, not analog. Analog, you may choose longer L, but digital, invariably, you will be choosing the length of the transistor to be the technology node, which is 65. Then W will be 130 nanometer, something like that. So we are asking what should be the maximum value of W by L for access transistor. What is your guess? I mean, suppose you don't solve the problem by learning, right? Conceptually, what do you think? What should be? This should be strong.
At least smaller than the 2, because it needs to be weaker, the access needs to be weaker than the NMOS.
So not necessarily, that's why I asked, right? So it's not intuitive, so you have to solve for it. But yes, if you size it say small, at least W by L2, it will operate.
Right.
Yeah, it will operate, but here we can go a little bit more than that as well, because we are allowed to go up to VT. Right, so you have to put in this context, because a good designer, right, want to make access transistor stronger, right, because as far as you can push it further strong, you are minimizing your read time. Your read time is very critical, right? So I mean, a safe designer will choose W by L for access transistor lower than 2. A safe designer, because then definitely read will be successful. But you want to also think about your other side, which is the read time. So you can see how far I can push it. Right? So it's not apple to apple. You have to find in the equation, right? That's why those equations are derived. So let's look at that one by one. So I think this is what all the equations are derived. So this is your starting point. W by L access by N is this. So here, for this problem, right, we know VDD, for example, one volt. VDD is 1 volt here, supply voltage. Threshold voltage is 0.35. So let's see, if I put this here, 1 volt, 0.35, 1 volt, 0.35, what is VQ bar I should put? VT. That's the only unknown, right? So for this problem, because maximum allowed, right, access will force VQ bar should be 0.35. So that's what you need to plug it in. So VQ, this is the first thing to understand. So in this case, for maximum allowed access transistor, I can allow maximum rise in the Q bar node to be 0.35. If I plug it in, your answer is like this. Access transistor is less than or equal to 3 times the NMOS transistor, not this one. So this is not intuitive, right? That's why I tell you, you have to plug it in numbers. Okay, yes, we know access transistor has to be weak, but how much? That depends on all those details. This is your governing equation now. Okay, any question? Can anyone simply tell me why it is not 1? I mean, what you yourself, right, Yonan?
Yeah.
So what you said is intuitive. If I were in your place, I would have also guessed it should be at least lower than 2. Right? But why can anyone tell me intuitively why it is not the case? Because operation mode is different, right? NMOS access transistor is operating in saturation, whereas NMOS is operating in the linear region. So linear region is already weak. So NMOS, right, the pull down NMOS is operating in a weaker regime. The current equation, if you look at, right, which is the underlying assumption for deriving this equation, is access transistor is operating in the saturation, which is stronger mode, and the pull down NMOS is operating in the linear regime, which is the weaker mode, right? So that's why you can allow, right? So that's this access transistor to be 3.9 times of your NMOS. So I mean, this equation, right, how it derives, based on that you can find it out. And second thing is you are allowing saturation, your VQ bar, right, to high voltage, the threshold voltage. So you are allowing to rise the node, right? It's not like to be 0 or very close to 0. So the more you allow it, this ratio or this number will be higher. Okay, so I think that's the thing. So your access transistor exactly value will be 2 times 3.7, which is 7.4. So that will be your maximum allowed access transistor. Questions, comments here? So this is the one limit, VQ should be less than VT, but you may keep, okay, I don't want to go at VT. I want to keep the read disturb voltage to 0.2 volt, so 0.1 volt, suppose. This is a safe design, right? Because when you are at 0.35, there can be some flip at some extreme condition. So if that is the case, then you will see access transistor has to be much smaller. This is the maximum allowed you can go. Okay, so that's the second part of the question. Is this one. This is the safe design. That okay, I'll make access transistor at 2 equal to my NMOS transistor. So these are problems 2. This was the problem 1 we solved. What is the maximum allowed W by L, which is 7.4, right? So this is A is 7.4, B is the safe design. And what you want to find? Find is delay, because both has different delay. Which one will have higher delay? The safe design. Safe design will have higher delay. But the aggressive design, right? This is more like an aggressive design. You are making access transistor stronger in this case, right? That will have much lower delay. So that's why you have to think all these parts. Okay. So now you have to plug in those numbers to find out what is the delay between A and B. So let's look at the answers. So yours, in one case, cell ratio is always access by, something is wrong, looks like. It should be NMOS by access, I think. I'll take a look. Okay, so this is for part A. This is the equation you need to start with to find delay. The bitline capacitance, change in voltage, and ICEL. So here change in voltage is 0.15. That is determined by your sense amplifier. Sense amplifier requires at least 0.15 voltage drop or voltage difference, right? So that is one constraint. So you plug it in here. Bitline capacitance is given 2 picofarad. Plug it in here. And ICEL. That is where you need to think. But that is where the mistake can happen. With ICEL, what current you will be using? It is an equilibrium current you have to use. And equilibrium current depends on VQ bar. So for A, what is your VQ bar? VT. That's what we derived, right? For A is the extreme aggressive design. So VQ bar is your threshold voltage. So that's what you need to plug it in your equation, right? So VQ bar is VT, 0.35. From that you can find VGS, plug it in VGS here. So you can find this is your 149.9 or 150 microamp. That is your ICEL, cell current, given by your VQ bar, equilibrium value of VQ bars. That is the difficult part, right? To find ICEL. So I hope you understood why we use VT here. VT equal to, because this is the equilibrium point based on which we derive the 7.4. So in this case, time comes around 2 nanoseconds. Because this is an aggressive design. Questions, comments here? Make sense? Okay, now let's look at the other part, B. For B, you have to find VQ bar. Right? For A, it was because we just solved the question number 1, that's why we know it. We can plug in. But for B, you have to use this equation. This is your starting point. Starting point, you find out what is VQ bar given the W by L ratio. W by L ratio is 1 plus 1. 1 plus 1 equal to these numbers. So VQ bar comes around 0.19 in this case. It will be lower than 0.35 because this is more like a safe design. But your time, if you now plug in current is now low, 95 microamps. So delta T comes 3.2 nanosecond. So that's the trade-off. So you can make your read stable, but at the expense of slower read. If you want to do faster read, your read can be unstable in some cases. That's the trade-off. Questions, comments? Okay, maybe I'm going a little fast, but please read through the slides. There are a lot of comments I made. And also homework 2 will be posted after today's class because very similar type of problems you will be using. This kind of same approach. Okay, now let's look at one more problem and I think we'll be done. So it's basically continuation of the same problem. So talking about the same parameters, threshold voltage 0.35, supply voltage 1 volt, NMOS transistors 2. Now we want to find maximum allowable PMOS transistor size. We have sized already XS and MOS. XS we know can be go as large as 7.4 or safe will be 2. Now how about NMOS? sorry, how about PMOS? How we'll size them? We'll assume mobility is 3 times, and NMOS mobility is 3 times in PMOS, not 4. Typically, people use 4 times or, yeah, so let's assume in this problem 3 times the PMOS mobility. So problem 1 means access transistors are already designed, which is the aggressive design, 7.4. Given this is 7.4, given this is 2, what is the PMOS? Maximum PMOS, because if you make PMOS, should not be maximum, it should be minimum PMOS size. Because if PMOS is very, very large, oh sorry, yeah, this is the maximum. Because if PMOS is very strong, then right will fail. Right? So PMOS, maximum value of PMOS you have to find given all those sizes. Yeah. Okay, so that's the problem. So let's look at again the current equation. So we talked about the one transistor will be operating in saturation, which is the PMOS, and access transistor in this case will be operating in the linear regime. So when you equate this current, you can start with directly with this equation. The PMOS size and MOS size is less than or equal to this, where this threshold voltage comes in because you want to go VQ, right? This is actually VQ. VQ is at least threshold voltage, so the right takes place. So that's where you can get PMOS size should be 2.3 times of access transistor size or low. You can design PMOS to be weak, that's okay. So these factors comes because of mobility ratios and all those different modes of operation and all, right? So that's account for this. So you can start with this equation directly in an exam or homework. With this equation derived based on this 2 current mode. Okay, so that's pretty much I think for PMOS. So plug it in, access transistor is 7.4 in one case, another case it was 2. So for both the cases you can find what is the maximum PMOS size. I think I'll stop it here today, and maybe in the next class we'll continue and finish SRAM discussion. Yeah, so, but if there's any questions, comments, I'll be happy to answer.
Extreme case.
For the safe design,
Make this guy have a bigger.
Yeah, that was
When this voltage starts increasing, we're actually increasing our overdrive, and we're jumping. So we still hit equilibrium, even though this is bigger WIL. This is directly, and then we move this voltage to this for a change because overdrive. This one's overdrive is set, it's just BDS increases. I understand. So that's why this one says quick form still get I messed up.
and also you can allow them to increase. The more you increase the voltage,
Yeah.
Right, yeah.
so that's why I mean
Fine tuning.
intuitively I will answer the same. It has to be lower than the strong one, you can say, but it has to be how much it is. Those kind of details.
Yeah,
Doing the specs is hard.
And that's a big deal.
So
If you make it 7.4 times.
Yeah, that's it.
That's a big deal. 1.5 nanoseconds.
Yeah, that makes sense.
Good will also.
For it to be possible.
How do you decrease the VQ less than the N2 will be turned off, right? Like Cuba won't be switched during the write operation. During the write operation, we are saying that B2 should be less than 80 N2.
Yeah.
But it won't flip the Q bar, or will it?
The moment it goes below,
Below threshold, it will flip.
yeah, it will flip.
And that's what you need to do. So what is your equilibrium double try? Then equilibrium, I mean, if you don't, well, should always be fun.
I agree, especially for us. Take notes. It's the first like 5 slides of my and it's all about like there's too much text on the slide to write on the slide. I mean, that's what he's saying because you're trying to write something. And there's only 5 million equations, and it's like okay, equations are really if you just you fold his like 5 pages of algebra. It's like okay, sure. That's also kind of scary because homework 1 was not as hard as like. Yeah, I know.